everyone. Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about remainders and introduce the idea of modular arithmetic. Let's get started with a easy problem here where we want to do some multiplication. So we want to find the last two digits of 143,000. So we have 143,252. And we want to multiply this by 202,155. So we want to find the last two digits of this at the end. Now, we all know how to do multiplication here, right? So we focus on our first digit, 5, right here first. Right, so 5 times 2 is 0. We're going to carry the 1. 5 times 5 is going to be 25. Carry the 1 is a 6, so we carry the 2. Right, so we carry the 2. Then we have 10, 12, carry the 1, dot, dot, dot. Right, we're going to continue along that there. Right, now we move on to the second 5 here. Right, I know there's some stuff missing, but we can kind of check out that in a second. But here we have, okay, we start with our 0. Then we have 5 times 2 is 0 again. We carry that 1 again. 5 times 5, right? We have the 6 again. So this is starting out very similar. Dot, 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 there. Now, why do I have the dot, dot, dots? Well, remember, we're looking for the last two digits anyway, right? So we just want those last two digits in the problem right off the bat. And so notice our last step here, right, is going to be to add up these numbers. And the reason I put the dot, dot, dots is that those don't matter. We can already see just by what we've done that the last two digits are going to be 60 in this case. And right, this shouldn't surprise you too much, right? When we're doing these algorithms for adding, multiplying, if we care about the last two digits, really only those last two digits are what matter in this case as well. Let's look at another example like this, right? These last digits are ones people are a little bit more comfortable with and make a little bit more intuitive sense. Let's look at the last digit of 3 to the 2021st power. Well, let's just start listing some powers of 3. Right? So what are the different powers of 3 we have in this case? So we could kind of list them out here, right? So we have 3, then we have 3 squared is 9, 3 cubed is 27, to the 4th power is 81, then we have 243. If we wanted to go one further, we would have 729 in this case there. Now, if we focus on the last digit again, right? So if we focus on our last digit, we can kind of see if we can find a pattern in this case. And again, if you think about this as every time we raise it to a higher power of 3, we're really just multiplying by 3. So we have 3, we have 9, we have 27, which is 9 times 3. But then all that matters is the last digit, so that's 7. Well, 7 times 3 is 21. Notice that 21 and 81 have the last digit, right? The same last digit, it's 1. That pattern doesn't matter if we're worried just about the last digit. 81 times 3 is 243. Notice 1 times 3 also is 3, the same last digit. 3 times 3 is 9. That's also the 729. And right, we can be pretty confident then that this same pattern is going to continue. 9 times 3, 27. We have a 7 and then a 1 in this case there. Right, so for a lot of these last digit ones, right, which is really we're going to see expand to other ideas with general remainders, you want to just be looking for the pattern we have. So this pattern repeats every 4 terms in this case. Now, right, what about 2021? right? So this pattern repeats every 4 terms. 2021, it's not so hard to say. Let me say 2021 divided by 4. We don't care about the exact number here, but if you want the exact number too, it's not so bad, right? This is 505 with a remainder of 1. And really that remainder of 1 is what's important here, because our pattern, right, repeats every 4 terms. So 3971, 3971. So when we get to the 2020th term, we're going to be at the last number in the pattern. We're going to have a full pattern ending in 1. So when we have a remainder of 1, that means we want the first term in the pattern there. And that tells us that the last digit of this number is just going to be 3. So 3 to the 2021st power is just 3 in this case. So we have our pattern. Once you find the pattern, you can then use that to determine where you are in the pattern and come up with our answer there. Okay, let's start to talk about modular arithmetic then. Now, these ideas are not different than what we've seen before. But when you do enough of these things, it's helpful to have some shorthands, right? A lot of math is about writing things down in convenient ways, right? Introducing ideas that have nice consequences, save time when you're doing stuff. So if two numbers A and B have the same remainder when divided by m, right? So all of this stuff is really talking about remainders in this case, but we introduce here a little bit of notation in this scenario, and we say that they're congruent or equivalent modulo m. So we have A triple line B mod m, and we can say this as A is equivalent to B modulo m. You might also hear A is congruent to B modulo m in this case. So it's a convenient way to talk about remainders in a lot of scenarios. So some kind of simple examples here, right? If we're talking about mod 10, we're talking about the last digit. So we could say 2021 is equivalent to 1 mod 10 because 1 is the remainder when we divide 2021 by 10. Likewise, 27 is congruent or equivalent to 2 mod 5. So they have the same remainder. 27 is 25 plus 2, and so that is our remainder in this case. Now we would also have things like 21 is 3 mod 9 here. Now I want to do a little bit of a caution. A lot of the time we will use mods and use this to specifically talk about remainders. A lot of our examples today will be talking about remainders. But as far as this notation is concerned, just to make that clear here, we also have examples like 27 is equivalent to 7 mod 5. Remember, this means they have the same remainder, right? You could take this and say they're both equivalent to 2 mod 5, right? So both of these things are equivalent to 2 mod 5. But by our definition, the way we define this, as long as they have the same remainder, they are equivalent mod m. So 27 has remainder 2, 7 has remainder 2 when we divide by 5, so they are equivalent mod m in this case. So that's a little bit of our notation here. Let's practice this with an example with and without our notation here as well. We want to find the remainder when 95 times 125 is divided by 9 in this case. Now, we can just do this the long way. You can multiply it out, you can divide by 9. Actually, if you look back at our kind of previous video about dividing by 9, that was an earlier Thursday tidbit. We have a trick for finding the remainder when you divide by 9. There's a trick for finding the remainder when you divide by 11 using the digits and stuff. those will be linked below. But right, let's practice a little bit thinking about remainders and working with remainders like we have been in this video today. So first thing I want to do is just write things out with the remainders. I'm going to do this the long way first and then kind of the shortcut with our modular arithmetic ideas. But I think it's helpful to see it written out the long way so you start to see why some of the things we're going to talk about on the next slide actually work. And this one example provides a pretty good idea of what's going on in general for these scenarios there. So I first want to write these out in terms of quotients and remainders, right? So 95 is 90, 10 times 9 plus 5. 125 is 13 times 9 plus 8. So if we're just talking about their remainders, they would be 5 and 8. But I want to keep track of their quotients here a little bit. Now, why is that? Well, one way then to multiply this out, so 95 times 125 then. Let's actually write this out like I have above with our quotients and remainders, and then use FOIL to multiply it out. And when we use FOIL, something kind of magical is going to happen when we talk about the remainders when we're dividing by 9, or when we're thinking about what's kind of left over when we divide by 9 in this case. So when we FOIL this out, our first term is 10 times 9 times 13 times 9. I'm not going to kind of fully simplify this because I want to keep the powers of 9 separate. So we have 130 times 9 squared. Then outsides, we are going to have 10 times 9 times 8. So there we are going to have 80 times 9. And then for the insides, right, we have 5 times 13 times 9. So we have 65 times 9. And then we have 5 times 8, so we have 40 in this case. Now, remember we are looking for the remainder. Our end goal here is to find the remainder when we divide by 9 in this scenario. So what's nice about this, if we just care about the remainder when we divide by 9, isn't this whole term with a 9 squared not going to matter? Right? Isn't this 80 times 9? That doesn't matter. That's divisible by 9. This is divisible by 9. All we have to worry about is our 40. Just the 40 matters in this case. Right? So if we look then at the remainder, right? The remainder here when we divide by 9 is 40, but that itself we have to worry about simplifying. Right? So when we simplify this, 40 has a remainder of 4 when we divide by 9. So we can kind of multiply it out with our powers of 9 separate, and then we see that they don't matter in this scenario there. So that's kind of how we can work with this when we kind of work with the quotients and the remainders in this case. Now, remember I said a lot of this stuff we can think of as being shortcutted, or kind of we have shortcuts when we're doing modular arithmetic. So let's do pretty much the same thing then in this case. So let me write my first line now in some of our modular arithmetic notation. What we're saying here is that 95 is actually congruent to 5 mod 9. They have the same remainder when we divide by 9. Likewise, we have 125 is congruent to 8 mod 9. And what we demonstrated above, basically, what this kind of showed the work for, in a sense, is that when we're doing this multiplication, all that matters is those equivalents in this case. So when we do 95 times 125, and if we're doing this mod 9, we only need to care about the remainders. The remainders are 5 and 8. So actually when we're multiplying, this is equivalent to 5 times 8 mod 9. And then that is equivalent to 40, which as before is equivalent to 4 mod 9. So I don't want to say this is doing something totally different. These are doing basically the same calculations both ways. But right, once you're comfortable with this pattern, this modular arithmetic, kind of the rules and also the definitions allow us to kind of save some of that work, right? We know all of this 10 times 9 and 13 times 9 stuff doesn't matter, so we just ignore it. We just focus on the 5 and 8. That's 40, which can be simplified to 4 in this scenario. This is really where that name modular arithmetic comes from, right? Two words there, modular and arithmetic, right? Arithmetic is kind of telling us that these arithmetic operations, arithmetic operations like plus, minus, times, division is a little bit spooky. So let's not focus on that one too much, but adding, subtracting, multiplying, they all work when we're doing mods in this case. What does that mean? That means, like the previous example, if we're working mod 9, if we want the remainder when we divide by 9, we can replace everything by remainders when you divide by 9 here. What is the remainder when 10 to the 2021st power plus 3 to the 2021st power is divided by 16 in this case? So let's think about this one a little bit and see what's going on here. First of all, we're working when we do divided by 16, right? So when we see this divided by 16 here, that's our clue that we're basically going to be considering stuff mod 16 in this case there. Now, this example, right, there's a little bit more going on. We have two terms. We can deal with those terms separately and things like that there. So let's first deal with the 10 to the 2021st power there. You can find patterns, you can look at stuff that way, but don't forget some of your other ideas and some of your other kind of knowledge points from number theory as well. For example, 10 is 2 times 5. So this is straight up equal to 2 to the 2021st power times 5 to the 2021st power in this case there. Well, wait a second then. 2 to the 4th power is 16, right? We have a huge power of 2 times 5 to the 2021. Isn't this divisible by 16? Yeah, so this is just straight up equal to 0 mod 16. So you don't always have to find patterns. You don't always have to look for patterns. You could see, write out a couple of the terms and see that eventually you get a bunch of zeros, and that's fine here. But right, you can also just use some of your other knowledge. We can see this is just divisible by 16, so it's going to be 0 mod 16 here. Now, let's do something similar for the powers of 3. Now, I want to start with an observation there. And sometimes, right, again, you can do this with a pattern, but sometimes it might just be helpful to kind of think about the numbers involved and think about powers of 3 a little bit. So we have 3, 9, 27, 81. Now let's think about 81 for a second. What do we know about 81? Well, it's 80 plus 1. 80 is 16 times 5. So we can actually say here that 3 to the 4th power, right, is equal to 81. And that is equivalent to 1 mod 16. And this is where then, right, you could have done this with patterns. I'm going to phrase the pattern stuff a little bit different here as well. Because now when we write 3 to the 21st power, practicing writing this out in mods and stuff a little bit. Well, first of all, this is 3 to the 4th power. So let me write this as 81. So we have 81 raised to the 505th power here. times another 3 in this case. So where does this come from, right? We saw before 2021. Let me write this off to the side here, right? 2021, remember, is when we divide it by 4, this is equal to 505 with a remainder of 1. All right, so we saw this kind of earlier today too, but it's good to kind of remind us of that fact here again. So we're kind of using that fact here to break it down into 81 to the 505 times 3 to the first power there. Now let's do our equivalents. 81 times 81 times 81, that's just a bunch of ones, right? So this is 1 to the 505 times 3, which is of course just 3 if we're working mod 16 in this case there. So what about our kind of original expression then? All right, so now we're ready to finish everything up here for our kind of final answer on the bottom. When we write everything out now, 10 to the 2021st power plus 3 to the 2021st power, right, is congruent to, when we're doing mod 16, right, our first power we said was 0. 10 to the 2021st was 0 mod 16. 3 to the 2021st is 3 mod 16. So this is 0 plus 3 mod 16, which is of course just 3 mod 16. And because, right, that is a valid remainder, then we're all set, right? So this then is our kind of remainder when it's divided by 16 here. So our remainder of this expression when we divide by 16 is just going to be 3. Okay, that will do it for today's video. Check back each week Thursday for a new math tidbit this year. And if you're looking for some other practice, check out ziml.areteem.org for free daily problems, other practice resources. We have monthly contests there too. Lots of great videos and resources there too. If you like this, please hit the like button, subscribe. Otherwise, I will see you all next week. Goodbye.